using a fusion reactor. An advanced civilization uses a fusion reactor to maintain a high temperature on a spherical blackbody whose radiation supplies energy for use on a spacecraft. The blackbody has radius r equals 1.23 meters and is surrounded by a larger sphere whose inside surface is densely lined with photocells, as you can see in the figure. These capture all photons that have energy within 1% of a central value E0. The photocells are designed so that E0 corresponds to the peak energy radiated from the blackbody. The range delta E is sufficiently small that we can approximate the spectral emittance as constant over the range E0 plus minus delta E. This device generates an EMF across a motor of resistance 1 kiloohms. Part A. The spectral emittance I equals integral I as a function of lambda d lambda can be structured as integral of I as a function of energy dE by parametrizing the integral using E is equal to hc over lambda. Use the Planck radiation law to determine I as a function of E. Be careful with the differential factor. So let's remember the Planck radiation law. Intensity as a function of wavelength is given as 2 pi h Planck's constant c square divided by lambda to the fifth power e to the hc over lambda kt minus 1, and the spectral emittance I is integral I of lambda d lambda. Now we're parametrizing this with energy E, so we're substituting E is equal to hc lambda to minus 1, hc over lambda. In other words, we're substituting lambda is equal to hc divided by the energy E. So that d lambda is going to be minus hc divided by E square dE. Okay, so we can now write intensity as a function of energy. The top was 2 pi hc square, so that stays as 2 pi hc square. So let's do that here. 2 pi hc square divided by lambda to the fifth power. So it is h to the fifth power c to the fifth power divided by energy to the fifth power. E to the hc over lambda is energy E divided by kt minus 1. Now you can see that this c square will make this c to the fifth power c cube, and then here we have h to the fifth power. That's going to become h to the fourth power. So we obtain the spectral emittance I is equal to integral I of E dE to be the integral 2 pi energy to the fifth power, because this e to the fifth power goes upstairs, divided by h to the fourth power c cube exponential energy divided by kt minus 1. And for d lambda, we're substituting this. So we have minus hc over e dE. Now you can see that this c will make this c cubed c squared, and this h will make this h to the fourth power h cubed. So finally, we obtain for the spectral emittance I is equal to minus 2 pi divided by h cubed c squared integral so here we had e square, so this is going to make this e to the fifth power e cubed also. So we will have 2 pi over h cubed c squared e cubed divided by exponential energy divided by kT minus 1 dE. So the minus sign here basically reverses the integration limits. So we have obtained for the spectral emittance the intensity as a function of energy E. That's what we were trying to find, to determine I as a function of E. So we can now read this I as a function of E in the integration 2 pi E cubed divided by h cubed c squared exponential energy divided by kT minus 1. So we have obtained intensity as a function of energy rather than as a function of wavelength. Let's move on to part B. Determine the energy E0 that maximizes the intensity and determine the maximum intensity in terms of the temperature T. Hint, you have to solve the equation 3 minus x is 3 times e to the x. Use the solution x equals 2.821, which is accurate to 4 significant figures. Let's see if that comes up here. So in order to find the maximum energy, maximum intensity energy, the IDE at that point must be equal to 0. So what is the IDE evaluated at E0? So we have the derivative of the top multiplied by the bottom. So e cubed derivative is 3e squared multiplied by the bottom exponential e over kt minus 1 minus the derivative of the bottom multiplied by the top. Derivative of the bottom is 1 over kt, because it's exponential e over kt. We have the derivative of the top, which is 1 over kt. So we will have minus e cubed divided by kt times e to the exponential e over kt divided by the denominator squared e to the e over kt minus 1 squared, and then we have this constant factor here, 2 pi divided by h cube c squared. And when this is evaluated at E0, we should obtain 0. So let's define x to be E0 divided by kt. Okay, so here we will have 3E0 squared, so E0 is xkt. So this is going to be 3 kt square x square. E to the E0 over kt is e to the x minus 1 minus e cube over kt. E cube is x cube kt cube. Kt cube x cube divided by kt e to the x, and this must be equal to 0. And here we have this kt cube becoming kt parentheses squared. So we obtain 3 kt parentheses square x square e to the x minus 3 kt parentheses square x square minus kt parentheses square x cube e to the x is equal to 0. And now we can divide it by x square. So we have 3 kt parentheses square e to the x minus 3 kt parentheses square minus x e to the x kt parentheses squared is equal to 0. And now we can divide it by kt parentheses squared. It will give us 3 e to the x minus 3 minus x e to the x is equal to 0, which means we're getting 3 minus x times e to the x equal to 3, which means we have 3 minus x is equal to 3 times e to the minus x. And we're given the solution of this equation. Then we can substitute as the solution of this equation, which was given here, the solution of 3 minus x is equal to 3 e to the minus x. X is equal to 2.821, so that we have E0 is equal to 2.821 kT. That's the maximum intensity energy. And what's the corresponding maximum intensity? It is the 2 pi energy cube, so it is 2 pi 2.821 kT parentheses cube divided by h cube c square exponential 2.821 minus 1, and that finally gives us, for the maximum intensity, I max is equal to 2.843 pi kT cube divided by h cube c square. That's the maximum intensity given in terms of temperature, which is what we were after in part B. Determine Imax in terms of temperature T. Okay, so in the first two parts of the problem, we have first written I of lambda as I of E by doing the substitution. Lambda is equal to HC over E, but this I of lambda will be used in the spectral emittance calculation. It will be replaced by I of E dE. So therefore we have to be careful. D lambda is minus HC over E squared dE. So if I just directly go from lambda to energy with this substitution, I obtain this. But then if I also include the d lambda minus HC over E squared dE, I obtain the following form. And in this form, this prefactor is I of E, which is the intensity as a function of energy. Now, the IDE is equal to 0 at E0 gives me the maximum point in the intensity at energy E0. And solving this by doing the substitution x is equal to E0 over KT, we find that x should be 2.821, which means the highest probability, the maximum intensity is for the energy 2.821 kT, and if we substitute that into this intensity, we obtain the maximum possible intensity as a function of temperature, 2.843 pi kT parenthesis cube over h cube c square.